Article 551.73c permits the application of demand factors to both the individual load and the total load. However, I note cautions against using demand factors in areas of extreme temperature. In locations where high temperatures are expected, it is generally not advisable to apply demand factors. The high temperatures could potentially result in the actual load exceeding the calculated load using demand factors, leading to voltage drop issues. To ensure proper voltage levels, voltage drop calculations should be performed to determine the appropriate wire size for the dedicated feeders. Without applying demand factors, the voltage drop calculations may dictate the use of a wire size that is too large for the lugs of a 50 ampere breaker. Since applying demand factors may not be prudent, alternative solutions should be considered to reduce the voltage drop. Firstly, installing additional distribution panels can reduce the distance to the loads, resulting in lower voltage drop. Secondly, some manufacturers offer circuit breakers with larger lugs that can accommodate thicker wires. This could allow using a smaller wire size for the dedicated feeders while maintaining adequate voltage levels. Thirdly, installing a voltage regulator at the main service entrance can help maintain consistent voltage levels throughout the system, reducing the impact of voltage drop. It is recommended to avoid applying demand factors in this case due to the potential for exceeding the actual load in high temperature conditions. Instead, consider installing additional distribution panels or exploring other options to reduce voltage drop while maintaining the desired 50 ampere service. When performing voltage drop calculations, there are several factors to consider beyond just the demand factors and temperature. These factors contribute to the overall voltage drop in the system and should be carefully evaluated to ensure proper performance and safety. One of the critical aspects is the length of the feeder conductors. The longer the distance between the source and the load, the greater the voltage drop. This is because the resistance of the conductor increases with its length, causing a larger voltage drop for a given current. Therefore, it is essential to accurately measure or estimate the length of the feeder conductors to use in the voltage drop calculations. The material of the conductor also plays a significant role in voltage drop. Copper and aluminum are the most common conductor materials used in electrical systems. Copper has lower resistance than aluminum, meaning it will have less voltage drop for the same current and length. However, aluminum is lighter and less expensive than copper, so it is often used in larger conductors where the weight and cost savings are significant. When using aluminum conductors, it is important to use appropriately sized conductors to compensate for the higher resistance. The cross-sectional area of the conductor, which is typically expressed in American wire gauge AWG or circular mils, directly affects its resistance and current carrying capacity. Larger conductors have lower resistance and can carry more current without overheating. Therefore, selecting the correct conductor size is crucial for minimizing voltage drop and ensuring the safe and reliable operation of the electrical system. Voltage drop calculations typically involve determining the minimum conductor size that will limit the voltage drop to an acceptable level under the expected load conditions. The current flowing through the conductor is another critical factor in voltage drop calculations. The higher the current, the greater the voltage drop for a given conductor size and length. Therefore, it is essential to accurately estimate or measure the maximum current that the feeder conductors will carry under normal operating conditions. This may involve considering the connected loads, their duty cycles, and any potential future loads that may be added to the system. The power factor of the load also affects the voltage drop in the system. Power factor is a measure of how effectively the electrical power is being used. A power factor of 1 indicates that all the power is being used to perform work, while a power factor less than 1 indicates that some of the power is being wasted due to reactive loads, such as motors and transformers. Reactive loads cause the current to be out of phase with the voltage, which increases the overall current flow and voltage drop in the system. Therefore, it is important to consider the power factor of the loads when performing voltage drop calculations. If the power factor is significantly less than 1, it may be necessary to correct it by installing power factor correction capacitors. The type of wiring method used can also affect the voltage drop in the system. Different wiring methods have different impedances, which can contribute to the overall voltage drop. For example, conductors in a steel conduit will have a higher impedance than conductors in a non-metallic conduit due to the magnetic properties of the steel. Similarly, conductors that are bundled together may have a higher impedance than conductors that are spaced apart. Therefore, it is important to consider the wiring method when performing voltage drop calculations and to use appropriate dating factors if necessary. The operating temperature of the conductors can also affect their resistance and voltage drop. The resistance of a conductor increases with temperature, so higher operating temperatures will result in greater voltage drop. The National Electrical Code (NEC) provides tables that specify the allowable ampacities of conductors at different temperatures. It is important to ensure that the conductors are not operated above their rated ampacities, as this can lead to overheating, insulation damage, and increased voltage drop. The acceptable voltage drop limits are typically specified in the NEC and other applicable standards. The NEC recommends that the voltage drop on feeder conductors should not exceed 3%, and the voltage drop on branch circuit conductors should not exceed 5%. These limits are intended to ensure that the voltage at the load is sufficient to provide proper performance and prevent equipment damage. When performing voltage drop calculations, it is important to use accurate and reliable methods. There are several methods available for calculating voltage drop, including the following. Firstly, the simplified formula method. This method uses a simplified formula to calculate voltage drop based on the conductor length, current, and resistance. This method is relatively easy to use, but it may not be accurate for complex circuits or circuits with nonlinear loads. Secondly, the voltage drop calculator software. There are many software programs available that can be used to calculate voltage drop. These programs typically use more sophisticated algorithms and can account for a wider range of factors such as conductor type, wiring method, and power factor. Thirdly, the NEC tables and examples. The NEC provides tables and examples that can be used to calculate voltage drop. These tables and examples are based on the NEC recommended practices and are a good starting point for performing voltage drop calculations. In addition to performing voltage drop calculations, there are several other steps that can be taken to minimize voltage drop in the system. These steps include, firstly, using larger conductors. Increasing the conductor size will reduce its resistance and voltage drop. This is often the most effective way to minimize voltage drop, but it can also be the most expensive. Secondly, shortening the conductor length. Reducing the distance between the source and the load will reduce the voltage drop. This may involve relocating equipment or adding additional distribution panels. Thirdly, improving the power factor. Correcting the power factor of the loads will reduce the current flow and voltage drop in the system. This can be done by installing power factor correction capacitors. Fourthly, using a higher voltage. Increasing the voltage of the system will reduce the current flow for a given power level, which will reduce the voltage drop. However, this may require replacing equipment and modifying the electrical system. Fifthly, using separate feeders. Providing separate feeders for large loads will reduce the current flow in the other feeders, which will reduce the voltage drop. Sixthly, balancing the loads. Balancing the loads on the different phases of the electrical system will reduce the neutral current and voltage drop. Seventhly, using voltage regulators. Installing voltage regulators can help maintain consistent voltage levels throughout the system, reducing the impact of voltage drop. When selecting conductors for an RV park electrical renovation, it is crucial to choose the correct type and size to ensure safety, reliability, and compliance with the National Electrical Code (NEC). Here is a detailed discussion of conductor selection considerations. Firstly, conductor material. Copper and aluminum are the two most common conductor materials used in electrical systems. Copper has higher conductivity and lower resistance than aluminum, making it a better choice for minimizing voltage drop and carrying higher currents. However, aluminum is lighter and less expensive than copper, making it a more economical option for larger conductors. When using aluminum conductors, it is essential to use appropriately sized conductors and terminations that are rated for aluminum to prevent corrosion and overheating. Secondly, conductor size. The size of the conductor is determined by its ampacity, which is the maximum current it can safely carry without overheating. The NEC provides tables that specify the allowable ampacities of conductors based on their material, insulation type, and operating temperature. When selecting conductor sizes, it is important to consider the expected load, the ambient temperature, and any dating factors that may apply. Dating factors are used to reduce the allowable ampacity of conductors when they are installed in certain conditions, such as in conduits or in high-temperature environments. Thirdly, insulation type. The insulation type of a conductor is determined by its voltage rating and its ability to withstand heat, moisture, and other environmental factors. The NEC specifies different insulation types for different applications, such as THHN, THWN, and XHHW. THHN insulation is commonly used for dry locations, while THWN insulation is suitable for wet locations. XHHW insulation is suitable for both wet and dry locations and has a higher temperature rating than THHN or THWN. Fourthly, voltage rating. The voltage rating of a conductor is the maximum voltage it can safely withstand without insulation breakdown. Conductors used in RV park electrical systems should have a voltage rating of at least 600 volts to provide an adequate margin of safety. Fifthly, grounding conductors. Grounding conductors are used to provide low impedance path for fault currents to return to the source, which helps to protect against electric shock and equipment damage. Grounding conductors can be either bare or insulated and should be sized according to the NEC tables. Sixthly, bonding conductors. Bonding conductors are used to connect different metal parts of the electrical system together to create a common ground potential. Bonding conductors should be sized according to the NEC tables and should be installed in a manner that provides a reliable electrical connection. Seventhly, conductor identification. Conductors should be clearly identified with their voltage, ampacity, and function. This can be done using color-coded insulation or by labeling the conductors with tags or markers. Eighthly, terminations. The terminations of conductors should be properly installed and tightened to ensure a reliable electrical connection. Terminations should be rated for the type and size of conductor being used and should be installed according to the manufacturer's instructions. Ninthly, conduit and cable. Conductors should be installed in conduit or cable to protect them from physical damage and environmental factors. The type of conduit or cable used should be suitable for the location and application. For example, underground conductors should be installed in rigid metal conduit or Schedule 80 polyvinyl chloride conduit to protect them from moisture and corrosion. Tenthly, surge protection. Surge protection devices (SPD) should be installed to protect the electrical system from voltage surges caused by lightning or other transient events. SPD should be installed at the main service entrance and at any subpanels that serve sensitive electronic equipment. 11th, arc fault circuit interrupters (FSIs). FSIs are designed to protect against electrical fires caused by arc faults. FSIs should be installed on all branch circuits that serve receptacles in RV parks. 12th, ground fault circuit interrupters (GFCIs). GFCIs are designed to protect against electric shock by detecting ground faults. GFCIs should be installed on all receptacles that are located near water, such as in bathrooms, kitchens, and outdoor areas. 13th, overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect conductors from overloads and short circuits. Overcurrent protection devices should be sized according to the ampacity of the conductors they are protecting. 14th, accessibility. Conductors and electrical equipment should be installed in a manner that provides easy access for maintenance and repairs. Clearances should be maintained around electrical equipment to allow for safe working conditions. 15th, labeling. Electrical panels and equipment should be clearly labeled to identify the circuits they serve. This will help to prevent confusion and errors during maintenance and repairs. 16th, documentation. A complete set of electrical drawings and documentation should be maintained for the RV park electrical system. This will provide a valuable resource for future maintenance and upgrades. 17th, compliance with codes and standards. All electrical work should be performed in accordance with the NEC and other applicable codes and standards. This will help to ensure the safety and reliability of the electrical system. 18th, qualified personnel. Electrical work should be performed by qualified and licensed electricians who have the knowledge and experience to perform the work safely and correctly. The NEC provides specific requirements for RV park electrical systems, including requirements for service equipment, feeders, branch circuits, and receptacles. It is important to be familiar with these requirements to ensure that the RV park electrical system is installed and maintained in accordance with the NEC. Article 551 covers electrical requirements for recreational vehicles and recreational vehicle parks. Some key aspects of Article 551 include: firstly, definitions. Article 551 provides definitions for terms such as recreational vehicle park, and recreational vehicle site. Secondly, general requirements. Article 551 outlines general requirements for RV park electrical systems, including requirements for wiring methods, grounding, and bonding. Thirdly, services. Article 551 specifies the requirements for service equipment in RV parks, including the size and location of service disconnects and overcurrent protection devices. Fourthly, feeders. Article 551 provides requirements for feeder conductors that supply power to RV sites, including requirements for conductor size, voltage drop, and overcurrent protection. Fifthly, branch circuits. Article 551 specifies the requirements for branch circuits that serve receptacles and other electrical equipment at RV sites, including requirements for receptacle spacing, GSI protection, and OFSI protection. Sixthly, receptacles. Article 551 provides requirements for receptacles that are installed at RV sites, including requirements for receptacle type, rating, and location. Seventh, recreational vehicle site equipment. Article 551 outlines requirements for electrical equipment that is installed at RV sites, such as power outlets and distribution panels. Eighth, wiring methods. Article 551 specifies the allowable wiring methods for RV park electrical systems, including requirements for underground wiring, conduit, and cable. Ninth, grounding and bonding. Article 551 provides detailed requirements for grounding and bonding RV park electrical systems to ensure electrical safety. 10th, overcurrent protection. Article 551 specifies the requirements for overcurrent protection devices, such as circuit breakers and fuses, in RV park electrical systems. 11th, voltage drop. Article 551 addresses voltage drop considerations in RV park electrical systems to ensure that adequate voltage is available at the RV site. 12th, surge protection. Article 551 recommends the use of surge protection devices to protect RV park electrical systems from voltage surges. 13th, inspections and testing. Article 551 requires that RV park electrical systems be inspected and tested to ensure compliance with the NEC and other applicable standards. Demand factors, as described in Article 551.73 and Table 551.73, are multipliers used to estimate the actual load on an electrical system based on the assumption that not all connected loads will operate at their maximum rated capacity simultaneously. Applying demand factors can reduce the calculated load, potentially allowing for smaller conductors and equipment. Firstly, permissibility. Article 551.73c allows the application of demand factors to both individual loads and total loads in RV parks. This means you can apply a demand factor to the individual load at each RV site, as well as to the total load on a feeder supplying multiple sites. Secondly, caution. The note accompanying Table 551.73 cautions against using demand factors in areas of extreme temperature. High ambient temperatures can increase the actual load in the system, potentially exceeding the calculated load based on demand factors. Thirdly, dedicated feeders. Even with dedicated feeders to each pedestal, demand factors can still be applied to each individual load, as permitted by Article 551.73c. However, this should be done with careful consideration of the potential for high temperature conditions and the actual load characteristics of the RV that will be used in the park. Fourthly, local conditions. In South Georgia, where high temperatures are common, it may not be prudent to apply demand factors. The actual load may exceed the calculated load, leading to voltage drop and other issues. Fifthly, voltage drop. If no demand factor is applied, the voltage drop calculations may dictate the use of larger conductors, such as 1/0 American wire gauge AWG, which may not fit under the lugs of a 50 ampere breaker. Sixthly, alternatives. To address the voltage drop issue without applying demand factors, consider the following. Firstly, additional distribution panels. Installing additional distribution panels can reduce the distance to the loads, resulting in low voltage drop. Secondly, larger breaker lugs. Some manufacturers offer circuit breakers with larger lugs that can accommodate thicker wires. This could allow using a smaller wire size for the dedicated feeders while maintaining adequate voltage levels. Thirdly, voltage regulators. Installing a voltage regulator at the main service entrance can help maintain consistent voltage levels throughout the system, reducing the impact of voltage drop. Seventh, conductor sizing. When sizing conductors for RV park electrical systems, it is important to consider the following. Firstly, load calculation. Accurately calculate the load based on the expected usage patterns and the potential for high temperature conditions. Secondly, voltage drop. Perform voltage drop calculations to ensure that the voltage at each RV site is within acceptable limits. Thirdly, ampacity. Select conductors with an ampacity that is sufficient to carry the calculated load. Fourthly, NEC requirements. Comply with all applicable NEC requirements for conductor sizing and installation. 8. Other considerations. Other factors to consider when designing RV park electrical systems include: firstly, surge protection. Install surge protection devices to protect against voltage surges. Secondly, GFCI protection. Provide GFCI protection for all receptacles that are located near water. Thirdly, FSI protection. Provide FSI protection for all branch circuits that serve receptacles in RV parks. Fourthly, accessibility. Ensure that all electrical equipment is accessible for maintenance and repairs. Fifthly, labeling. Clearly label all electrical panels and equipment. By carefully considering these factors, it is possible to design an RV park electrical system that is safe, reliable, and compliant with the NEC. The NEC provides specific requirements for overcurrent protection in Article 240. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors and equipment from overloads and short circuits. Firstly, purpose. The purpose of overcurrent protection is to prevent damage to conductors and equipment caused by excessive current flow. Secondly, types of overcurrent devices. The NEC recognizes two main types of overcurrent devices. Firstly, circuit breakers. Circuit breakers are electromechanical devices that automatically interrupt the flow of current when an overload or short circuit occurs. Circuit breakers can be reset after they trip, allowing them to be used repeatedly. Secondly, fuses. Fuses are one-time devices that melt and open the circuit when an overload or short circuit occurs. Fuses must be replaced after they blow. Thirdly, selection. The selection of overcurrent protection devices should be based on the ampacity of the conductors and equipment they are protecting. The NEC provides tables that specify the allowable ampacities of conductors and the maximum size of overcurrent protection devices that can be used to protect them. Fourthly, ratings. Overcurrent protection devices are rated in amperes and volts. The ampere rating indicates the amount of current the device can carry continuously without tripping or blowing. The voltage rating indicates the maximum voltage the device can safely interrupt. Fifthly, location. Overcurrent protection devices should be located at the point where the conductors receive their supply. This helps to protect the conductors from overloads and short circuits that may occur downstream. Sixthly, coordination. Overcurrent protection devices should be coordinated to ensure that the device closest to the fault will trip first. This helps to minimize the extent of the outage and prevent unnecessary tripping of upstream devices. Seventhly, accessibility. Overcurrent protection devices should be accessible for inspection, testing, and replacement. Eighthly, labeling. Overcurrent protection devices should be clearly labeled to indicate the circuit they protect and their ampere rating. Ninthly, NEC requirements. The NEC provides detailed requirements for overcurrent protection, including requirements for conductor protection, equipment protection, and coordination. Tenthly, specific applications. The NEC also provides specific requirements for overcurrent protection in various applications such as RV parks, marinas, and healthcare facilities. Article 250 in the NEC covers the requirements for grounding and bonding electrical systems. Grounding and bonding are essential for electrical safety as they provide a low impedance path for fault currents to return to the source, minimizing the risk of electric shock and equipment damage. Firstly, grounding. Grounding refers to connecting the electrical system to the earth. This is typically done by connecting the neutral conductor to a grounding electrode, such as a ground rod or a metal water pipe. Secondly, bonding. Bonding refers to connecting different metal parts of the electrical system together to create a common ground potential. This helps to prevent voltage differences between metal parts, which can create a shock hazard. Thirdly, grounding electrode system. The NEC requires that all electrical systems have a grounding electrode system, which consists of one or more grounding electrodes. The grounding electrode system should be installed in accordance with the NEC requirements. Fourthly, equipment grounding conductor. The equipment grounding conductor EGC is used to connect the metal parts of electrical equipment to the grounding electrode system. The EGC provides a low impedance path for fault currents to return to the source, helping to trip the overcurrent protection device and clear the fault. Fifthly, bonding jumpers. Bonding jumpers are used to connect different metal parts of the electrical system together to create a common ground potential. Bonding jumpers should be sized according to the NEC tables and should be installed in a manner that provides a reliable electrical connection. Sixthly, metal water pipe. A metal water pipe can be used as a grounding electrode if it meets certain requirements. The water pipe must be in direct contact with the earth for at least 10 feet and must not have any insulated joint. Seventhly, ground rod. A ground rod is a metal rod that is driven into the earth and used as a grounding electrode. Ground rods should be at least 8 feet long and should be installed in accordance with the NEC requirements. Eighthly, concrete encased electrode. A concrete encased electrode is a grounding electrode that is encased in concrete. Concrete encased electrodes are typically used in new construction and should be installed in accordance with the NEC requirements. Ninthly, separately derived systems. Separately derived systems, such as generators and transformers, have their own grounding requirements. The NEC provides specific requirements for grounding separately derived systems. Tenthly, hazardous locations. Hazardous locations, such as those where flammable materials are present, have special grounding requirements. The NEC provides specific requirements for grounding electrical equipment in hazardous locations. 11. Grounding receptacles. Grounding receptacles are designed to provide a low impedance path for fault currents to return to the source. Grounding receptacles should be installed in accordance with the NEC requirements. 12th, testing. The grounding system should be tested to ensure that it is functioning properly. The testing should be performed by a qualified electrician. The NEC provides specific requirements for voltage drop in Article 210.19a on FPN4 and 215.2 AFI FPN2. Voltage drop refers to the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction, reduce the efficiency of electrical systems, and create a fire hazard. Firstly, voltage drop limits. The NEC recommends that the voltage drop on branch circuit should not exceed 3% to the farthest outlet for power, heating, and lighting loads, or combinations of these. Furthermore, the maximum voltage drop to the farthest outlet for power, heating, and lighting loads or combinations of these should not exceed 5%. For feeders, the NEC recommends that the voltage drop should not exceed 3%. Secondly, calculating voltage drop. Voltage drop can be calculated using the following formula: voltage drop equals current times resistance, where voltage drop is the voltage drop in volts, current is the current flowing through the conductor in amperes, and resistance is the resistance of the conductor in ohms. Thirdly, conductor resistance. The resistance of a conductor depends on its material, size, and length. The NEC provides tables that list the resistance of different types of conductors. Fourthly, conductor length. The length of the conductor is the distance from the source to the load. The longer the conductor, the greater the voltage drop. Fifthly, conductor size. The size of the conductor affects its resistance. Larger conductors have lower resistance and will result in less voltage drop. Sixthly, load current. The load current is the amount of current that the load is drawing. The higher the load current, the greater the voltage drop. Seventhly, power factor. The power factor of the load can also affect voltage drop. Loads with a low power factor will draw more current and result in greater voltage drop. Eighthly, minimizing voltage drop. Voltage drop can be minimized by using larger conductors, shortening the conductor length, reducing the load current, and improving the power factor. Ninthly, NEC requirements. The NEC requires that voltage drop be considered when designing electrical systems. The NEC also provides recommendations for minimizing voltage drop. Tenthly, specific applications. The NEC provides specific requirements for voltage drop in various applications such as RV parks, marinas, and healthcare facilities.